Okay, hello everybody. I'd like to welcome you all to Zygo's first webinar of the new year. You can see some GoToWebinar instructions on the screen. If you're not familiar with GoToWebinar, feel free on the right side to enter any questions you might have during the webinar. And we have staff members that are standing by and they'll answer you in chat. And if you don't get an answer, we'll make sure we follow up with you after the webinar. So with that, let's get started. We're going to talk today about characterizing film thickness and topography with coherent scanning interferometry. I'm Dan Rossano. I'm an applications engineer with Zygo. I'm based in our Connecticut headquarters. I've been with the company for about 7 years now. I work pretty heavily on our optical profilers that use coherent scanning interferometry. So I'm pretty excited to present today some advancements we've made in film measurement over, even just the time I've been working here. So let's start just by looking at that title. It's a bit of a mouthful. So what we're going to do is talk about characterizing film thickness and topography. So a film, as far as Zygo is concerned, is a material that's transparent to visible light, and it's thin enough for us to measure through. So visible light, because that's where our instruments operate. And by thin enough, we're typically talking about less than 100 microns or so. So something even like a glass microscope slide that might be a millimeter thick, or a bulk piece of something transparent, that's not a film. Really, we're talking about things that are thinner than that we might be able to focus a microscope through both surfaces. Generally with these samples, we want to measure the thickness of the film as well as the surface topography, so the roughness or dimensions of critical features. And so we're looking at more than one point. We want an area. And that's why coherent scanning interferometry is the technique of choice. It's a well-proven ISO-recognized surface topography tool. It's fast and aerial and non-contact. And so it's a well-proven technique. So brief outline, we're going to next move on to some background of coherent scanning interferometry, of films, and kind of the way the world was up until about 2015. After that, I'm going to introduce 4 different challenges that those films metrology methods face, and then 4 solutions that we've introduced since about 2015, in the last 5 years or so. Those are going to be measuring thin films, measuring rough films, bringing our films metrology to the production line, and then measuring larger areas of films. And after we cover those 4, we'll see if we have any questions, and we'll do maybe a brief Q&A, and we'll wrap up. So let's start with what is CSI. So many of you probably are familiar with the technique, but if you're not, coherent scanning interferometry is a technique where we take an extended broadband light source, which is just a way of saying something like an LED or a light bulb, and we combine it with an interference objective, and that's a microscope objective. So these systems typically are microscopes. Inside of that objective, there's a beam splitter, and that produces 2 beams when light travels through it. One of those 2 beams goes to our test object. The other travels to a reference mirror that's inside the objective. When the 2 beams recombine after reflecting off of their ultimate goal, they travel to the camera where they interfere with each other. And so we see a localized interference signal, and we're able to scan our microscope objective physically in the z-axis, and that will move that interference signal across the part surface. So that's what you can see in that video in the bottom left. And so because we have this localized signal, when we have 2 different points in the field of view of our microscope objective, if those points are at different heights, we will see a height difference in the location of where the peak of that signal is recorded. So essentially CSI comes down to scanning the microscope objective, collecting the signal over all of the pixels, and then analyzing them to determine where the peak of that signal is. And in a typical system, this might happen on 1 million pixels or more. So this technique, as I presented it, is pretty general. It can measure very smooth surfaces, like in the top left here, at an optically polished flat. It can measure rough or steeply sloped surfaces. In the top right there, that's a 40-degree cone. And then you can use it to measure large areas, to see very fine detail on optics, and measure micro features on microfluidics. It's a very general and versatile tool for measuring surface topography across all kinds of materials. But films can complicate that. So films are common with high-tech components that we run into, things that already require non-contact metrology, things like displays or optics or biomedical devices. And while film effects can be beautiful, things that cause this kind of rainbow effect of oil on a puddle, those same effects cause trouble for traditional optical metrology. And even if you only are interested in the top surface of a film or a part that is coated with a film, you still have to deal with those film effects. And additionally, very often we see applications that are looking to know more about the film itself, such as the thickness or the uniformity or the texture, perhaps of a substrate underneath a film. And so there's a whole bunch of traditional films metrology tools on the market that have strengths in different ways, but none of them really provide both the 3D surface information and the film profiling information. And so while CSI is a proven surface tool, we really want to make it capable of measuring films because that's a great opportunity to do robust 3D films metrology. And since about 2004, Zygo has been measuring what we call thick films. So a film that's thicker than about a micron produces a signal that looks like this one here, where instead of seeing a single localized signal in our scan, we see two distinct kind of lobes. And when those signals are well separated, as they are in this picture, they can be analyzed independently. So like I mentioned, we've been doing this at Zygo for over 15 years now. It's a kind of well-known method that produces really nice results. If you know information about the film, like the refractive index, that can be helpful, but it's not strictly required. And I mention that because it is in contrast to some methods we'll talk about later. So this technique has worked quite nicely. Essentially what we do is we calibrate using an optical flat. So we place our polished optical flat underneath our system and we measure it to create a prototype signal for the optics that we are currently using. Then when we measure a film, we can compare the prototype signal to the measured signal. And anywhere that we see that the prototype signal matches up pretty well with our measured signal, we recognize that there is a film interface there, and we can report the thickness and the top and bottom surface height. And by repeating that across our entire surface map for all of our pixels, we build up a map that shows both the top surface topography, the substrate topography, and the film thickness. But this method, while it works pretty well in the cases where it's appropriate, can fall apart in different regimes. So one of those is thin films, if films are less than a micron. And then there's a couple of others that we'll get to as we get further into the webinar. So with thinner films, the signals from the top surface and the substrate start to get mixed together. So no longer are they these two distinct separate signals that you can separate, and no longer does your prototype signal properly match in a way that gives you useful information. So the solution that Zygo employs is to instead predict the film signal with model-based CSI. So the general outline of this is that we have a technique where we can compute a model signal. That is what we expect the signal of our instrument to look like based on the specifics of the optics that we're using and the material of the film and the substrate. And then we vary the thickness over a range that the user chooses. And that range can be quite wide. And we compute a bunch of different model signals. We can then, after taking a measurement, compare the model signals that we've calculated to the measured signal. And only when you have a good strong match are you able to say that is the thickness of that film at that given pixel. And then repeat that across the entire field of view. And you're able to do the same thing that we did before, just in a way that is more precise and more complex. The trade-off here is that this technique, rather than using a generic prototype signal, requires knowledge of the refractive index of the substrate and the film. And that's both the real and complex part of the refractive index to account for any absorption effects. And there's other difficulties that need to be overcome, right? So this sounds very simple. You just model the signal, but that in itself is pretty difficult. You have to account for the optical system of your microscope, as well as the effects of possibly having high magnification on your signal. You have to model the effect of the film and the substrate's optical properties. And this, even once you've kind of created a theoretical model, is very computationally intense. So a typical search might include 1,000 or more model signals that you're comparing to 1,000,000 or more pixels. And generally, with CSI, we are really looking to keep the high speed capability. So we want measurements that take less than 5 seconds, kind of from beginning to end, just because that's what users have come to expect when they are doing measurements with this type of instrument. So fortunately, recent advances have enabled us to solve those problems and to provide general usage model-based CSI that creates full field maps of both surface topography and thickness across the entire camera array in less than 10 seconds for typical measurements and over the full range of objective magnifications. So that's from the very low mag 1x objective wide field of view up to the 50 or 100x magnification to view those very small features and very fine surface topography. And this model-based CSI leverages the hardware automation of the NextView and the NextView NX2 platform, and so is only available on those systems. What's great about this is that even with a very technically complex methodology to the measurement where we model materials and the system itself, there's a nice simple kind of 3-step user interface for setting up. First, you select your magnification, in this case, a 50x objective, and then you describe the part, whether it's silicon oxide on silicon or a gold overcoat or whatever it might be, and I chose those on purpose. And then you measure and you're able to get results right on the screen in just a few seconds. What's great about the model-based approach is that it supports very wide search ranges. You don't need a guess value. You don't need to worry about narrowing in on a potential value or getting incorrect results. So here we show a measurement at the edge of an oxide coating on silicon, where the thickness ranges from over 1 micron down to basically 0. Where the film is gone and there's only bare silicon. And so here we show that the model-based technique can support a wide search range and produce unambiguous results across that full range of 1,200 nanometers in the search. Next, we really want to make sure that this model-based technique is internally consistent, that it can handle multiple materials in the field of view, and we want to just put it through its paces. So one sample that we made to do that test, which does some nice demonstration of the capability, is this oxide on silicon trench sample. So we start with a silicon wafer that has thermal oxide grown on top to about a 1 micron thickness. Then we etch a trench into the oxide, but not all the way down to bare silicon. So now we have film that's 2 different thicknesses, and then we deposit an overcoat of gold, which is thick enough to be optically opaque. So this provides an interesting situation where we're dealing with different materials in the field of view. And why this is an interesting test is that even bulk materials can confuse conventional CSI. So when you reflect off of a material like glass or silicon dioxide, you get a phase change on that reflection. And the phase change is different than it is when reflecting off of a metal. And in fact, different metals all have unique, different phase changes. And this is important because our system is an interferometer and it measures the phase of the light. And so a phase change on reflection causes a step height change. And this is pretty obvious to anyone who's ever tried to measure a chrome on glass artifact. You'll see that metals tend to appear lower than they actually are. And so what's nice is that model-based CSI, because it's modeling the material properties, can correctly measure the surface topography for dissimilar materials and can correct for this phase change on reflection step height error. So we can kind of combine that into the measurement of this sample by customizing our measurement to treat the 2 areas, one as gold, a kind of opaque gold overcoat, and the other as the uncoated oxide over the silicon substrate. So here's the measurement results that we get from such a setup. We see the surface map gives us correct topography across dissimilar regions. The gold overcoat is slightly higher than the bare oxide. We see trenches of 2 different widths here, where the depth of the trench or the thickness of the film that's measured is slightly different, revealing that the etch process acts slightly differently in the different width trench. And we see, using the gold overcoated region, a good way to test if our film is properly measuring thickness. So by comparing the depth of the trench in the gold coated region with the bare region, we see a nice agreement to better than 1 nanometer of the depth of those trenches and the profiles across them. So that gives us some nice confidence in the technique. And indeed, if we measure from the gold area to the uncoated area, we see that same less than 1 nanometer agreement in measuring the thickness of the gold. And so we can be pretty confident that our technique is self-consistent and it produces reliable results. So this model-based technique will measure individual layers of thin film down to about 50 nanometers in ideal conditions. And like I mentioned, it's available for both the NextView and the NextView NX2 platform. And that's available now. So that resolves the issue of thin films, at least in a very large way. We're going to switch gears a little bit now to talk about some thick films applications and advancements. The first of which is dealing with rough films. So when we talk about measuring a rough surface, we run into problems pretty quickly because rough surfaces cause light to scatter. So looking at something like this additively manufactured surface, because it's so rough, our light scatters and we lose phase information in our measurement, and it weakens our signal. Fortunately, Zygo has done a lot of research in the last 30 years to make CSI much more capable on these very challenging surfaces. And if you have any experience with what our surface topography measurements have done in the last 10 years even, it's been leaps and bounds forward. But rough films have always caused a problem because they're just more complex. When there's multiple interfaces, there are additional challenges. And because we use that prototype signal matching method, it is prone to failure in cases like the one I show here. So this is a rough film. It's a transparent coating on an anodized aluminum surface. And you can see that the signal trace, here no longer a cartoon, this is an actual signal trace, shows the signal boxed in red. And that really looks nothing like the kind of prototype signal that we would expect from an optical flat. And so in many cases, you get data dropout on the film. Whereas in others, when we detect only the substrate, but not the top surface, we end up with what we refer to as a pinhole, where it looks as though the film has a very deep hole in it, but in fact, we're just seeing all the way down to the substrate underneath. So this is a pretty common issue with rough films, and it's not a very attractive looking measurement, something we definitely would want to improve. In addition, and this is for all films measurements, but is really exacerbated by rough films, is that there is a signal threshold that a user needs to tweak. So in the case of rough films in particular, you may have an expert user who needs to spend, maybe hours changing the signal threshold value, trying to let in just the right amount of data while still, rejecting any noise, and they're doing a lot of post-processing, and it's very time-consuming, and it's a very unreliable process. And so what we set out to do is to improve the performance on rough films, and also to try and remove this source of uncertainty for users who are trying to set up, a difficult films measurement. And so I'm pretty happy to introduce this robust thick film analysis. We are very happy to say that sometime in the first quarter of this year, we'll be releasing a software update that makes this available to all current films users. We've removed the signal threshold as a user input entirely. So there's no more need to tweak or toggle that value. And additionally, this improves the surface assignment, so you have no more pinholes, as well as the sensitivity and reliability of films measurements. So you can see kind of a before and after here, where now we've removed all that data dropout. We get a much nicer surface of our film without those deep pits in the surface. And then here's another example just showing a before and after of the same data with the new processing enabled. So on the top, that surface looks nice and flat. Obviously, it still has roughness to it, as it is a rough film. but good data coverage, no dropout. Whereas on the bottom in the old processing, it's a much worse looking measurement, which is kind of typical of what you'd expect trying to measure a rough film with the older method. So this is really a big step forward, and like I mentioned, that will be releasing soon, and it will be available to anyone who currently has a film's license for their instrument. Okay, so next we're going to talk about breaking films measurements out of the process lab or the development lab and out onto the production floor. So more and more, if you look at things like the next generation of LEDs or fingerprint resistant coatings on personal electronics, these types of film applications are moving into kind of large scale production environments. And so we really want to address two things. The first is the price of a traditional films metrology instrument. And then the second is the vibration tolerance. So for Zygo, we addressed both of those for typical surface metrology when we released the Z gauge, and then its follow-up, the Z gauge Pro. So this is an instrument that has a low cost, it's about half the price of a traditional CSI instrument, small footprint, has basically no facilities requirements except for power, and it's very vibration tolerant thanks to the SureScan technology that's available on all Zygo profilers. So with this instrument, we've demonstrated that you can really do sub-nanometer precision CSI anywhere. And now we can offer films analysis on the Z gauge, and films is now compatible with SureScan for all Zygo profilers. So that takes the same low cost, high performance surface metrology and extends it over to films. And the effect of that, even for a non-Z gauge instrument, can be pretty dramatic. So you can see here a measurement before and after the application of SureScan on a film surface. So this improves the new view and the next view's vibration tolerance as well. And it allows Z gauge and Z gauge Pro instruments to measure films down to 5 microns of optical thickness. So this is available as a software upgrade right now. If you have a Z gauge instrument or an instrument without films, you would need to add a films license. But otherwise, the capability is a standard upgrade available with our version 8.0 MX software. So this is a really big step forward in terms of reducing the barrier to entry, lowering the cost, and improving the performance all in one swing for films metrology, especially in production applications where you might want to be, right next to the line. So that's one that I think is very exciting. I'm looking forward to some of the doors that will open for Zygo profilers in the future. The last thing we'll talk about today are large area measurements. So in particular, this is keeping a high lateral resolution, maybe a high magnification objective, and looking at larger areas. And that has excuse me, traditionally required image stitching. So image stitching is a great technique for optical profilers and CSI. Much like how a phone has a panorama mode, we take multiple measurements and we can combine them together into a single larger image. And in one example here on the left, I'm showing a slope analysis view of a very fine scratch on an optical surface that could only be revealed by image stitching at high magnification. And then on the right, another example that just shows a 40 millimeter diameter that again, you could only capture by image stitching multiple tiles together. So these are some core applications of stitching that we see in the surface realm, but that's never really been a possibility for films because films measurements just produce such a more complicated set of data that stitching is just a more challenging task. But now we have also been able to enable stitching for films measurements. And what that means is when you take a stitch, and this here is a 5x5 stitch, so 25 total measurement tiles, you'll be able to stitch the top surface, which is the leftmost plot, as well as the thickness map. And note here how this sample only has a film in that central square, and the secondary surface or the substrate. And we don't see any stitch boundaries, no discernible tiles, as well as very high dynamic range in the measurement. So we can see, the macroscopic micron or more thickness of the film, as well as small scratches and defects in the surface as well. So we maintain that low noise, high precision measurement with our image stitching. And we can combine that with the other techniques that I spoke about. So here is a rough film that has been stitched. So this is a 15 tile measurement covering about 1 by 1.5 millimeters. What's really great about this measurement is you can see on the top surface measurement on the left, that cylindrical form where we measured the part, and a very similar cylindrical form on the substrate secondary surface. But when we look at the film thickness in the center, we don't see any curvature, because as you'd expect, the film has been evenly deposited, and so its thickness is roughly constant, except for this highlighted defect that we can see, which really you would have a hard time locating if you weren't able to do stitching and you weren't able to look over larger areas, just because that defect is about the size of one entire field of view. And you really need a nice reference area to compare it to in order to analyze that defect appropriately. So this is a nice example that brings together the robust rough film measurement with the image stitching. And in fact, we could do the same measurement on a Z-gauge system, which is shown here as well, just to tie all three of them together. So film stitching is available on any system right now with films analysis and motorized staging. So the motorized staging is a requirement just from a hardware perspective. Films analysis is an additional license. I hope you'll agree with me when I say that it's definitely worth having if you have any kind of films metrology needs. So any Z-gauge, new views, or next views. And it benefits from the robust films and SureScan capability. It is not compatible with model-based analysis or the advanced films, but if that's something you're interested in, definitely let us know. We're obviously committed to innovating in this space and to making sure that Zygo is always pushing the envelope forward, whether it be from the technical perspective or the user experience perspective. So that brings us to the end of the 4 challenges that we had: thin films, rough films, bringing films metrology to the production floor, and then measuring large areas that were covered in films. And I hope you'll agree that there are some really exciting solutions that Zygo has to offer for these challenges. There's obviously always going to be more challenges out there as people come up with new parts that they want to make and new requirements. So expect there to be more coming from us in coming years. But for now, that's the kind of state of the art in films metrology. I'll take a quick look at the questions here and see if we have a couple that would make sense to kind of answer as a group. Okay, so one question just about the kind of thickness of how thick a film can be. So if you want to measure a thicker film, you generally need to make sure that you can scan physically with your objective from the top surface all the way to the bottom surface. That usually means we want to be thinner than about 100 microns, but we do applications pretty regularly, especially with higher grade optical materials where we can measure through 1 millimeter or even more, just recognizing, of course, that there's always a trade-off once you're traveling through that much material. Okay, so we're going to end the webinar there. I want to thank everybody who joined me. If it's very early where you are, thank you for starting your day with me. If it's late where you are, thank you for joining me during dinner time. And I hope you have a good rest of your day or rest of your night, and look forward to more webinars in the future coming from Zygo. Thanks, everybody.